This is lesson 8. Just about fell over there. This is lesson 8, which looks sort of short, but it is it's abstract, and so we're going to sort of take a deep breath and think about this carefully. All right, so this covers chapter 3, sections 12 through 15. And I don't have my book with me, I lent it out, but I've got the general ideas in my head. What we need to do is we need to draw or recognize cyclohexanes with substituents in the axial position. Draw or recognize cyclohexanes with substituents in the equatorial position. Describe the effects of cyclohexane substituents on conformation stability. And then evaluate relative stabilities of substituted cyclohexanes. So first of all, we need to talk about what is meant by axial and equatorial. What is meant by axial and equatorial, and that's really where all of that's really where the key of really the heart of this lesson is. Before we do that, we need to describe what the pictures. Pardon me. Where's my vocabulary today? We need to sort of introduce the student to pictures and what is going to be meant by what picture. For example, with the last video, we introduced something called Newman projection formulas, and there's some things about Newman projection formulas which are not necessarily intuitive, and we described those in lesson 7. We need to do the same thing with cyclohexane. So if you're going to draw that, what would you draw? Would you draw some yellow sticks and pink sticks and green sticks and black, I don't know, what is that? A dodecahedron? Just a minute here. How many faces does that have? 1, 2, 3, 4, 6, 7, 14. I have no idea what no idea how many what that's called, but it's a black ball, right? Well, how would we draw that? Well, we wouldn't draw it like that. We've got to draw faster, and we've got to make sure that our notation is less dependent on good art. So we've got just the same as we have here, right? It's a circle and a few lines, and we can quickly say what we mean by with a few strokes of the pen. We can do the same thing here. So we have to first of all say, of course, I'm calling this cyclohexane, so this is going to be a carbon. These are 2 hydrogens right here, right? And this is a carbon-carbon bond. All right. So what we're going to do is we're going to talk about the way we're going to draw that. And we're going to draw this from a side angle, and I'm going to draw these 2 bonds right here, these 2 which my fingers are touching, okay, parallel first. And then if I'm drawing it like that, I'm going to draw that one carbon, which my hand is now touching, up here, and the other carbon down like that. Okay? It's important to know that these things can go through ring flips, which of course is part of this lesson for lesson 8. And what that means is that these bonds are constantly have the ability, they're sigma bonds, right? So they can constantly go back and forth. So here's an example of this thing going back and forth. And obviously we have a bond breaking right there. So, all right. So it's the reason why I've got 2 different colors of sticks here is to show you that if this thing is in, let's see, this was the confirmation of it right here, right? Can you see how all the pink sticks are pointing up or down? Or they're perpendicular to the average plane of this ring? And the green ones are sticking sort of out. Not exactly straight out, but sort of out, okay? Now watch this. When this goes through a ring flip, if this is the head, I'm going to call that carbon the head, this is the head, and that carbon the tail, right? If that head goes down and the tail goes up, then all of a sudden the greens are perpendicular to the plane of the ring. Okay? Now we're going to call these green positions here axial because they're parallel to the axis. This is the axis of the ring. And these are called equatorial because they're sort of like the equatorial, right? They're not exactly straight out, but all right? So these are axial and these are equatorial. So what I've got here is all the greens are in the axial position, all the pinks are in the equatorial position. If we go through a ring flip, then all of the other ones, right, go into the axial position, and the green ones are in the equatorial position. Okay. So that's the first thing that we've got to establish. Now the question is, you've got to be able to recognize with a picture. The first objective is to draw or recognize cyclohexanes with substituents in the axial positions. So what we can do is we can say now all of a sudden, let's let all these be methyl groups instead of hydrogens. So it's no longer cyclohexane, but instead it's 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, dodeca, methyl, cyclohexane. If these are all methyl groups, it's going to be that, right? A big mess. So this methyl group now is in the axial position. This one's in the equatorial position. All right. So here's what we're going to do. When I'm doing this, I'm going to say, can you see how this carbon is up above the relative plane of this ring, or the average plane of this ring, and this carbon's below it? Up, down, up, down, up, down, up, down. Can you see that? Okay. So everyone that's up, its axial is going to be like that. You see, perpendicular to the average plane of the ring. That one's up. That one's up, and that's it. Those are the only three that are up, right? The other three are down. Let's do these as, let's do them down, down, and down, right? And let's do a different color for the equatorial. When I'm drawing this, I'm going to draw them straight out. Okay, 1, 2, I missed one. Boom. I guess that one probably should be going that way, but all right. 1, 2, 3, 4, 5, 6. All right, and that is what I've got here. It looks like the pinks are in the equatorial position, so let's do a ring flip. The pinks are in the equatorial. There's the head up, right? I'm letting green be that one right there, and that picture is that. Okay, and when this goes through a ring flip, you're going to have to be able to do this. It is not a resonance structure, by the way. It is indeed a real flip. So what I'm going to do when I do a ring flip is I'm going to keep these two bonds of the deck the same. I'm just going to put that one guy down because he was up, and this guy up because he was down. Okay. Now I know, and this I'm just going to memorize this, that if this was in the equatorial position before, it's going to be in the axial position afterwards. So up, 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 down, 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 right? And these blue, if it was in the axial position before, it's going to be equatorial afterwards. So remember, this bond was this bond, same bond, right? And this bond was this bond. Okay? So these are all going to be, right? And last night in class, I drew this as a wedge and a wedge because it's coming out toward us, and a hash, which is fine, probably more precise. But you can imagine the picture is going to get pretty busy if we worry about that too extensively. Okay, so that's objective number 1. And that is drawing things in the axial, in the equatorial position, or recognizing them as such. If this looks easy, you may be in for a surprise. It may be more difficult than it looks. If it looks difficult, then I would say the same thing. You're going to have to do this. You're going to have to do it yourself. My recommendation is to do it with a model and to draw them out. And after you've done it a bunch of times, then it gets I'd say routine. Okay, now we have to describe the effects of cyclohexane substituents on conformational stability. All right, this is going to be relatively simple. I'm going to put some substituent here. I don't want to name this because it's a bit ugly, okay? Put some substituent here, and I'm going to say that if this is in the axial position, this is the higher energy position. And the reason is because it's got all these interactions with these other guys here. Okay, it's got, see that? This is going to be flopping around. So the axial position is the higher energy position, higher energy. The bigger it is, the more it wants to be in the equatorial position. Okay, so this guy's got more room to flop around out here. Yes, there's still interactions like that, but there are fewer interactions. Okay, up here, they're all closer. Okay, so the main point of this is axial higher energy. Axial is equal to higher energy. Okay? And that's the second objective for this video. And let's do the third objective now. Let's do two different ones, a big one and a small one. Can you see the difference in these two sizes here? Let's just call them big and small, okay? Well, you know what? You guys are sophisticated enough. We can call this ethyl and methyl. Okay? Can you see an ethyl group here? Boom, boom, 2 carbons, right? Suppose that's a CH3, I guess, of course. Can you see a methyl here? That'd be a CH3. CH2, CH3, okay? Well, in this conformation, it is in the, and I'm going to draw this, okay? This is in the equatorial, or rather axial, so I'm going to say that's ethyl, and that's methyl, right there, okay? Hydrogen, 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 All right, that's that. Where the ethyl is here, with the head up, you see that? These two bonds are these two bonds here, okay? And the ethyl is in the axial position, and the methyl is in the equatorial position. And when I'm doing this on a quiz or exam, I'm going to make notes. I'm going to label it, okay? Bigger is an axial, all right? But if we do a ring flip, so I'm going to keep these two bonds the same. I'm going to bring this one up and that one down. If we do a ring flip, then that's going to be, I'm going to draw the axials first because they're always easier to see. Then the ethyl is going to be in equatorial position, and this methyl is going to be in an axial position. Okay? Which is better? These are all hydrogens. Let me not finish that out. Which is better? Bigger in equatorial or bigger in axial? And the answer is, if axial is higher energy, and if the issue is steric hindrance, then we want bigger in the axial position. Lower energy. We're generally going to call lower energy better. Okay? All right, and the one final question I'm going to leave you with is if we can draw cyclohexane like this. Now, suppose I say in a question stem, this is cyclohexane, and it's in the lowest energy conformation. If that's cyclohexane, this is a hard question, and I'm going to leave you with it. If this is the lowest energy conformation, can you read that? That's methyl here. Okay? And everything else is hydrogens. Is this axial? And is this axial? That's the question. Okay? Please be ready to answer that in class tonight. I notice I gave it to you in different notation here, okay? But still, this is unambiguous. Still clear, even though we haven't looked. You haven't looked at it a whole lot, but we have. I'm going back to previous lessons to describe what we mean by that. Okay. Good luck.